Welcome to AI Paper Podcasts. Today, we are looking at a brand new paper titled WorldStereo.
Bridging camera-guided video generation and scene reconstruction via 3D geometric memories.
Yeah, that's the one, by Yisu Zhang and a team from Zhejiang University and Tencent Hunyuan.
Right, and to give you the one-minute summary right up front, current foundational video diffusion models generate visually stunning videos, but they fail completely at 3D consistency when you try to explore different camera trajectories.
They just warp.
Exactly. So WorldStereo solves this by acting as a powerful world model that bridges camera-guided generation and 3D reconstruction. It uses two novel modules.
Okay, what are they?
First, a global geometric memory, or GGM, to inject coarse structural priors via incrementally updated point clouds. And second, a spatial-stereo memory, or SSM, which enforces fine-grained detail consistency using explicit 3D correspondences.
Wow, okay.
Furthermore, it leverages a modified distribution matching distillation, or DMD, to accelerate inference to just 4 steps.
4 steps. That is, if you are an ML engineer or an AI researcher listening, this is a massive leap forward. We're talking about taking a single perspective image, or even a panoramic image, and turning it into a highly faithful, fully explorable 3D world.
It really is a fundamental shift. We're finally moving away from relying on models that just hallucinate pretty pixels frame by frame.
Okay, let's unpack this. We need to look at the fundamental gap these researchers are addressing.
Right.
Because if you look at the current landscape of foundation models, massive players like Hunyuan Video or Cog Video X or WAN, their visual quality is undeniably incredible.
Oh, absolutely. Photorealistic.
But if you take those generated frames and try to stitch them into a 3D scene, maybe using Gaussian splatting, you almost always end up with this ambiguous, blurry mess. The paper points out that they suffer from what they call memoryless visual conflicts.
Yeah, memoryless is the perfect word. That's the exact bottleneck the industry has been hitting.
Because they just don't remember the space.
Exactly. A diffusion model trained on millions of 2D videos understands what a living room generally looks like, but it doesn't inherently track the spatial coordinates of every single object in that room across time.
Right.
So when the camera pans around a coffee mug, the model literally forgets what the other side of the mug looked like in the first frame. The handle might just melt into the cup.
Or the text on it turns into alien symbols.
Right, exactly. And the existing workarounds for this memoryless problem just fall short.
Like the long by VDMs.
Yeah, the researchers classify those as long by VDMs, where they attempt to generate these long camera trajectories in a single massive pass.
Which seems logical, right?
The thought process makes sense on paper. If you generate everything at once, the model can look at the whole sequence and keep things consistent. They rely on the bidirectional global attention of diffusion transformers.
But there's a hardware reality check there.
A massive one. DITs scale quadratically with sequence length. Because every token has to attend to every other token, doing this at high resolutions requires prohibitive computational costs.
So you end up sacrificing quality.
You have to. You sacrifice overall video quality or resolution just to get the sequence to fit into the GPU memory.
Which kind of defeats the purpose of using a high-fidelity foundation model in the first place. The other common approach I see developers using is autoregressive, or AR models.
Right. Generating long videos sequentially.
Predicting the next frames based on the previous ones.
And AR models bypass that memory limit of generating everything at once, but they introduce a different set of severe issues. They inherently lack precise camera control.
Why is that?
Because they're predicting forward in a latent space that doesn't strictly adhere to real-world physics. But more importantly, they suffer from catastrophic error accumulation.
Oh, because if the model hallucinates a tiny geometric error in frame 10.
By frame 100, that error has compounded exponentially.
And suddenly your straight walls are curved.
The floor is tilted, gravity is broken.
Yeah, I think anyone who has worked with generative models knows that pain. There's really nothing more frustrating than getting a beautiful sweeping drone shot, only to realize that when you try to extract a mesh from it, it looks like it was filmed by a pilot who forgot how physics works.
It's an optical illusion in 2D.
Exactly. So how does WorldStereo actually build a reliable blueprint that doesn't drift?
It starts with a very solid frozen base architecture. WorldStereo builds upon Uni3C, which is a camera-guided VDM based on the WAN I2V foundation model.
Okay, so it leaves that massive brain untouched.
Completely untouched. It uses a lightweight control net branch to steer it. When you give the system a single input image, It first extracts point clouds using a state-of-the-art monocular depth estimator called MOJ.
So Moj calculates the depth at every pixel and projects it using the camera's intrinsic matrix, giving us that initial real-world metric scale 3D prior.
Right, it tells the model how far away the couch is from the wall in that first frame.
But single frame depth isn't enough for long sequences, as we just said. It'll eventually drift.
And this is where their first major innovation comes in, the Global Geometric Memory, or GGM.
So how does the GGM build on that initial depth estimation?
What's fascinating here is the mechanics of what they call the 3D cache.
The 3D cache, okay.
Rather than just relying on the initial reference points from that first frame, GGM incrementally reconstructs a global point cloud for each new video segment the model generates.
While it's generating.
Yes. As it creates new frames, it feeds them into a feed-forward reconstruction method called WorldMirror to extract new point clouds.
Oh, I see.
And the true brilliance of the GGM is how it handles long sequences by seamlessly merging overlapping views from these disparate 3D caches.
They mentioned using the Umiyama transformation for that merging process. If my linear algebra isn't failing me, that's the math used to perfectly align two different point clouds, right? By finding the optimal rotation, translation, and scaling until they click together.
That is a perfect way to visualize it, yes. By constantly applying this transformation, the GGM updates its global point cloud.
So the model is never flying blind.
Never. It's continuously referencing a globally consistent map of the space it's generating.
It sounds exactly like building a physical scaffolding. The GGM provides the model with this constantly updating, structurally consistent 3D blueprint.
Exactly.
Because it knows exactly where the walls and objects are in 3D space at all times, it can generate multiple consistent video trajectories from that single starting image. The paper even notes that this robust global memory supports full panorama-based 3D generation.
Which is huge.
You can input a 360-degree panorama, and the GGM will maintain spatial integrity as you explore that entire panoramic space.
That is a massive achievement for virtual reality and game design applications. But structural scaffolding only gets you part of the way there.
Right.
GGM is phenomenal for preserving the overall coarse geometry, making sure a wall stays flat or a table doesn't sink into the floor.
But point clouds are sparse.
Very sparse. When you rely solely on GGM, the generative model can start to lose high-fidelity details.
Because scaffolding is great, but nobody wants a structurally perfect 3D room if the wallpaper looks like a melted painting.
Exactly. The textures on a brick wall or the intricate pattern on a rug, they'll start to morph or blur across different camera trajectories. The point cloud just doesn't hold enough pixel-dense information to lock those textures in place.
Here's where it gets really interesting. How do they actually pin down the fine details and nail the textures?
They introduced the second memory module to work alongside the GGM, the Spatial-Stereo Memory, or SSM.
Okay, the SSM.
While the GGM acts as a 3D cache for geometry, the SSM relies on a 2D memory bank.
A 2D memory bank.
Yeah, as the video generation progresses, this memory bank stores temporally downsampled versions of the generated video frames.
Building a library of high-resolution reference views.
Precisely.
But wait, how does it know which pixels in the new frame correspond to the specific textures in that stored memory bank? I mean, if the camera is moved 10 feet to the left, the pixels are in completely different places on the screen.
This is where they drew inspiration from traditional stereo matching. In classic computer vision, stereo matching finds corresponding pixels in two images taken from different viewpoints to estimate depth.
Right, like how our eyes work.
Exactly. The SSM flips this concept to learn spatial coherence. It uses the point map data stored in the GGM's 3D cache to establish explicit mathematical connections between a newly generated target view and the retrieved reference views from the 2D memory bank.
So it maps the 3D coordinate of a pixel in the new view back to the exact same 3D coordinate in the reference view, even if the camera angle is completely changed.
Yes. And it doesn't just pass this information to the model as a gentle suggestion.
It forces it.
The SSM actively constrains the model's attention-receptive fields. In the cross-attention layers of the diffusion transformer, it forces the query tokens of the new target view.
The pixels asking, what should I look like?
Exactly, those pixels. It forces them to focus specifically on the key and value tokens of the explicitly corresponding regions in the retrieved reference view.
Oh, wow. It's essentially tying the model's hands and saying, don't hallucinate this texture, copy it directly from the memory bank.
That hard constraint perfectly preserves fine-grained details across extreme camera movements.
I noticed a really interesting detail in their methodology. regarding the training data they used for this SSM module.
The misaligned sampling.
Yeah, because obviously to train a model to do this kind of spatial retrieval, you need multi-view video pairs. But perfect, smooth multi-view data is incredibly hard to source.
Very hard.
So they got creative. They used existing multi-view data sets like Tartan-Air and DL3DV10K, but they created their training pairs through temporally misaligned sampling. They intentionally grabbed reference and target videos with only a 30 to 90% overlap.
Yeah.
Why make the training data intentionally messier?
That is actually a brilliant regularization technique. If you train a model on perfectly smooth adjacent temporal frames, it gets lazy.
Lazy how?
It learns to just copy the previous frame because the difference is so minimal. By forcing the model to find correspondences between frames that only partially overlap or are taken from wider, disparate angles, you force it to actually learn the underlying 3D spatial relationships.
They even applied random masking to the reference views during training, which simulates the messy, discrete, and incomplete nature of real-world image retrieval.
Right, the model has to rely on the actual 3D geometry to find its textures rather than taking a temporal shortcut.
It's a perfect example of how clever data curation solves complex architectural bottlenecks. You don't always need a bigger model. Sometimes you just need to design a harder test for it during training.
Couldn't agree more.
But adding these complex mechanisms, a 3D cache with global point clouds, a 2D memory bank, explicit stereo matching, constrained attention layers, that usually introduces a severe compute penalty.
Oh, typically it's a massive penalty.
Adding all of that usually makes a model agonizingly slow, which is an absolute nightmare for developers trying to deploy these systems at scale. Nobody wants to wait 3 hours to render a 5-second clip. So what does this all mean for inference time?
This is perhaps one of the most practical breakthroughs in the paper. They completely bypass the massive compute penalty by implementing an acceleration technique using a modified distribution matching distillation, or DMD.
Okay, unpack DMD for us. How does that work without breaking the model's ability to generate high-quality images?
To understand why it works, you have to look back at the architecture we mentioned earlier. WorldStereo strictly injects all of its pixel-wise aligned conditions, both the point clouds for the GGM and the retrieved reference views for the SSM, through that separate lightweight control net branch.
Meaning the base 1I2V video diffusion model remains completely untouched and frozen.
Exactly. They aren't retraining the massive multi-billion parameter DIT backbone.
Which is huge.
Because the base model is frozen, they can apply DMD to distill the complex model into a fast student network without needing to jointly train the entire massive architecture.
Okay.
DMD minimizes the KL divergence between the frozen real score function of the teacher model and the trainable fake score function of the student model.
Just to keep us grounded here, KL divergence is basically a way to measure the difference between two probability distributions.
Yes.
So instead of tweaking the massive brain of the model, they are just measuring how far off the fast student's guesses are from the slow teacher's perfect answers, and only updating those lightweight control net steering wheels to close that gap.
That is the perfect way to phrase it. The gradients only update the lightweight control branches. This prevents the catastrophic forgetting that usually happens when you try to fine-tune a foundation model for a highly specific task like 3D consistency.
So the base model retains all of its open domain generalization capabilities.
Right. It still knows what a cat, a sports car, or a medieval castle looks like.
But the control net branch is now guided to be spatially rigorous.
Precisely.
And what is the actual speed up from this distillation?
It drops the inference time down to just 4 steps.
Yeah.
To put that in perspective, the generation time goes from over 162 seconds in the base Unit 3C model down to just 9 seconds per video segment in WorldStereo.
9 seconds.
Yeah.
That is practically real time for high-fidelity, 3D consistent video generation. That completely changes the workflow for developers building interactive environments or iterating on game assets.
It's a game changer.
But of course, speed means absolutely nothing if the output is flawed or the geometry is warping.
This raises an important question regarding how to properly evaluate this.
Yeah, because standard video metrics like FVD or simple CLAP scores don't really capture structural integrity, do they?
They completely fall short. FED, or Friche video distance, might tell you that a video is temporally smooth and looks realistic on a frame-by-frame basis.
And a CLAP score just tells you it matches the text prompt.
Exactly. But neither of them will flag the fact that a wall shifted 3 feet to the left when the camera panned. FED cannot measure strict 3D geometric consistency across multiple camera trajectories.
So the industry didn't really have a ruler designed to measure this specific problem?
No, they didn't. To solve this, the authors had to build their own ruler. They curated a brand new 3D reconstruction benchmark specifically designed to test camera-guided VDMs.
Using what data?
They took established, highly rigorous datasets like Tanks and Temples and Mittner F360. They meticulously processed and cropped the ground truth point clouds from these datasets to serve as an absolute baseline for camera motion accuracy, 3D consistency, and trajectory fidelity.
That is a phenomenal contribution to the community all on its own. Having a standardized benchmark for VDM 3D reconstruction is going to push the whole field forward because now everyone has a common standard to test against.
It really is.
So how did WorldStereo fare against the competition on this new benchmark?
It comprehensively outperformed prior state-of-the-art models. They benchmarked it against strong models, like Voyager, Seva, and Gen 3C.
And the results?
Across the board, WorldStereo achieved significantly lower rotation and translation errors, meaning its camera control is vastly more precise. It maintained much higher trajectory fidelity, and it still scored higher on visual quality metrics.
So the explicit spatial constraints of the SSM combined with the global geometry of the GGM proved to be a winning combination.
Without a doubt.
The numbers are impressive, but the visual proof in the paper's supplementary materials is breathtaking. I want to paint a vivid picture for you based on what they showed.
The visual examples are incredible.
They really are. They tasked the model with generating highly accurate 3D point clouds of complex, occlusion-heavy subjects. For example, there's a sequence featuring a yellow toy bulldozer built from complex Technic parts. The reconstructed point cloud captures the intricate gaps in the treads, the mechanical arms of the front loader bucket, and the exact spatial relationship of the toy sitting on a textured mat on a wooden table.
And mechanical objects with fine gaps are notoriously difficult for diffusion models to reconstruct consistently.
Because the occlusions change drastically with even a tiny camera movement.
Exactly. If the model is just guessing, those gaps will fill in or shift around. The fact that the treads remain distinct proves the SSM is doing its job perfectly.
Another amazing example they show is a vintage, rusty blue flatbed truck parked in a city plaza.
Oh, I love that one.
The model captures the wooden slatted bed in the back, the rusty wheel wells, and even the San Pedro Square Market logo painted on the door.
Which is wild because text is usually the first thing to garble when a generative model tries to move a camera around an object.
Right. But the point cloud here is incredibly dense and geometrically stable, from a bird's eye view right down to an eye-level bumper view.
And they didn't just stop at individual objects either. They stress-tested the world model aspect on massive, immersive environments.
The environments are wild. There is a generation of a ruined, overgrown Gothic cathedral. You can see a broken skylight letting in volumetric rays, incredibly complex stone archways, completely covered in ivy, and a large circular hole in the floor leading to a lower level.
The point cloud maxed the entire interior volume flawlessly.
And perhaps my favorite is a sprawling, torch-lit underground dungeon. The model consistently reconstructs the flickering warm light against the rough, cold stone walls down long, twisting passageways.
Generating a long passageway from a single image is the ultimate test of error accumulation.
Because of the drift we talked about.
Right. Without the GGM's global point cloud, those dungeon passageways would have eventually curved or collapsed into themselves as the autoregressive drift took over.
And without the SSM, the intricate ivy on the cathedral walls or the logo on the truck door would have morphed into abstract noise as the camera moved closer.
It truly validates their dual memory approach.
To summarize the massive value of this research for you, WorldStereo proves that we no longer need to choose between the stunning visual quality of open-source 2D diffusion models and the strict geometric consistency required for actual 3D world building.
We can have both.
We are bridging the gap and doing it in 9 seconds.
If we connect this to the bigger picture, it underscores the sheer power of the generate first, then reconstruct a paradigm. By keeping the foundation model flexible and frozen, and injecting geometry-aware memory through lightweight, extremely fast distilled control nets, the AI community gets the best of both worlds.
It makes generating explorable 3D environments accessible, fast, and computationally efficient for developers.
Exactly.
And it opens up some wild possibilities for the future. I want to leave you with a final provocative thought to mull over. If we can successfully inject global point cloud caches and explicit stereo memories into diffusion models without retraining their base weights, What other physical priors could you patch into these foundational models next?
That's a great question.
Could we inject rigid body physics engines directly into a control net? Could we map real-world material properties like mass and friction into the attention layers so the model inherently knows how a pane of glass shatters versus how a rubber ball bounces? The architecture of WorldStereo suggests that to simulate true reality, we don't need to retrain the brain, we just need to give it the right memory modules.
It's an exciting time.
It really is. Thank you for joining us on this deep dive into WorldStereo. We will catch you on the next video of AI Paper Podcasts.